Okay, so welcome everyone to the afternoon session. And we have been reset back to resetting. So both talks will be about resetting. First, Martin Evans and then Arnab Pal. Okay, Martin.
Okay, so thanks, Priya. So first of all, I'd like to thank Sanjeev and Manju for the invitation and the organization. My talk today is the cost of stochastic resetting. So just to start with a very brief recap, we heard some nice talks on resetting yesterday. So the idea of resetting is that if you're looking for something and you're sort of searching in a random way and you're not finding what you're looking for example, your keys or something, then an obvious thing to do is to go back to where the keys should be, say over here, and to start searching again. And we heard yesterday that, yes, this actually can reduce the time to find the keys. And especially in the arena of a diffusive search process, then you can show that this is a good strategy. However, there's an obvious thing that's overlooked there, sort of an elephant in the room, is that my going back to start the search again implies some time, first of all, to get back to where I started, and some effort. I might have to clamber over something, or even David Dean mentioned, is this cost like an emotional cost? So there's various costs you could think of involved with the resetting. And that's the question I want to address today, is the cost. And no, that's not what I wanted. Yeah. So trying to make an objective cost for resetting and then study the statistics of the cost. So that's what I want to talk about. Now, I realize that looking at this just before the talk, some of the new slides are a little bit detailed and have some definitions. So please shout and ask questions if you're unsure of definitions and what I'm talking about. Yeah. Okay, so let's start. So the talk, I'm going to give a review again of the general idea of resetting. Then the particular approach I'm going to use is renewal approach, so I want to review that. We saw a bit of that yesterday. And then I actually want to make a little digression into stochastic versus deterministic resetting. So that's just a short bit. And then the main part of the talk is the cost of resetting. So I was reminded actually that, so this paper here, this is diffusion with stochastic resetting. We actually wrote this in India in January 2011. I was here, and I'd forgotten that. And you know, time flies. That's almost 13 years ago. That's crazy. Another Indian connection is that the main part of what I would talk about is this paper here, which appeared in Journal of Physics A. And John Sunil is a PhD student, and he's from Kerala, but he's settled in well to studying in Edinburgh. Okay, so as I've said, a good strategy for searching for keys or whatever is to go back to where they should be and to start the search again. And more generally, search problems is ubiquitous in biology. So the kind of search I'm talking about, you can translate into animals foraging for food. So the diffusive, if you like, part of the search is them foraging around, and then the herd will make large migrations where they essentially reset and go somewhere else and start again. And one can think of internet searches, etc. More general context, we can think of chemical reactions. Let's say there's something that an enzyme or catalyst should bind somewhere and set in train a whole sequence of complicated reactions. And these reactions may get stuck in the wrong place. And actually, there again, it can be shown that it's actually advantageous to be able to unbind the enzyme and start the whole complicated process again. Within computer science, the restart algorithm or general idea has been around for a while, and they can prove rigorously some sort of limited results. I also mentioned perhaps the earliest application was sort of in catastrophes, in population dynamics, where you can think of, let's say, some bacterial population growing and becoming more diverse, and then someone comes along with the antibiotic and kills them all off, and it goes back to normal, and you have this sequence of resetting to some sort of initial condition. So it's quite a general idea. And yeah, why does it work? So coming back to, let's say, the diffusive search, if I just wander around searching for something aimlessly, or well, not aimlessly, just mindlessly, I'm liable to sort of wander off, let's say, out onto the balcony, searching for my keys, and I'm not going to find them there. So that's sort of a bad trajectory which you can get into. And by resetting, just starting again, you essentially cut off those errant trajectories and those long time tails in the search. And that's generally a good thing. So that's how it works. And the arena within which it's easy to discuss this idea is diffusion with stochastic resetting. So that's what Satya was talking about yesterday. And we'll call this Poissonian resetting, which simply means there's a probability or a rate, which is probability per unit time of resetting. So it's just a constant rate R. And yeah, so then if we have a diffusive particle, so in one dimension we just think of the diffusive particle as searching, and it's looking for some target, and when it hits the target, the search is over. It's found the target, and it's over. So for the probability distribution, we have the usual diffusion equation for our diffusive searcher, and then the resetting introduces these two new terms here. So we have a loss of probability from any position x. Sorry, I should have said P of xt is the probability that starting from x naught we're at x at time t. And for the moment, I'm going to leave the target out of it for the moment. So we're just looking at the probability distribution with resetting. So we have a loss term from all positions x, and that probability from the resetting always, in the simplest case, goes into resetting to some fixed point x naught, which is usually taken to be the initial position. Now you can easily generalize this to resetting to some distribution. I'm just taking the simplest case here. That is just a position x naught you reset to. Yeah, so Satya mentioned yesterday that one interesting thing straight away is that this equation has a stationary state, and it's a non-equilibrium stationary state. So this is the second motivation for studying resetting, is to generate non-equilibrium stationary states. And I won't be focusing on that so much in this talk, so I won't put up a picture of that. But simply for diffusion, if we now, I'm going to, in a moment actually, add a target, the bottom line is that it's well known for a diffusive process, and the mean time to find some point, so if you're in, let's say, one dimension is the simplest case, then the probability that you reach some point is probability 1 at some point in time, but the mean time to get there is actually infinite. So that makes it a bad search strategy. But the moment that you switch on resetting, then that mean time becomes finite, and that's sort of the key idea and why it's so appealing. By simply having some resetting, you reduce an infinite expected search time to a finite expected search time. So all good. Right, so if I haven't skipped, no, that's good. So what I'm going to do now is to go into the slightly more detail of that, of showing that result. So I'm going to consider, again, thinking of our diffusive particle as the searcher, I'm going to now put in an absorbing target at the origin. So that's what it's looking for. And it's starting from x naught, which is away from the origin, and it gets reset there. And so now let's define Q as a survival probability. So that's starting, so x naught is the initial position, then after time t, that the particle has survived, which means it hasn't found the target yet. And, okay, as I've said, there's a resetting rate r to x naught and an absorbing target at the origin. And the subscript r here simply means this is in the presence of resetting. So the boundary conditions, well, if we start at the target, it gets absorbed straight away. It's found it straight away, so the survival probability is always 0. And at t equals 0, the survival probability is 1. So these are the two boundary conditions. Then, this is where it starts to get detailed, but actually we found that this is by far the simplest approach. And it's simple once you get the hang of it. It looks a little bit complicated first time you see it, but you write down some renewal equation. So in this case, it's going to be last renewal. And so the idea is, so we want the survival probability up to time t. And so one thing that could happen is that there might have been no resets at all. And the probability, because I've got Poissonian resetting, and it's a constant resetting rate, the probability that there's no resets in time t is simply this, e to the minus rt. And then I also need it to survive without resetting. And so this is why you see here I've got q naught. That means no resetting. So this first term is the probability of no reset and survival. So that's just a product of those two things. Then the other case is that there has been some resets, one or more, and we'll integrate over the time of the last reset, which is actually at time t minus t primed. So for there to have been a reset then, the probability is r dt primed, remember it's a constant rate, and then it has to not have any more resets until the end. So we have an e to the minus r t primed. Then it has to have survived with resetting up to t minus t prime, so get a q of r there. And then the final stretch, t prime, there's no resetting, so it's q naught, survived. And so it looks a little bit complicated, but once you get the hang of it, these are easy to write down and fun. Okay, you don't have to do too many calculations, you just have to get to the two terms right. And then, of course, the nice thing with this is that this has a convolution form. So this integral over t prime, I've got a t minus t primed and a t primed. Okay, there's a little e to the minus rt prime there, but that's okay. And so the way to solve this is just to take Laplace transform. Then this is going to factorize. And I'll spare you the details. It's only really, honestly, 2 lines. But you quickly get that your Laplace transform for the survival probability with resetting, you get it in terms of these Laplace transforms without resetting. And they are all classical results that, I mean, they're fun exercises to work out, or you can just look up a book like Sid Redner's book or whatever, and you'll find these expressions. So then sort of the problem is solved. So as I've said, you just require the Laplace transform of the survival probability without reset. So this is particularly simple when we have Poissonian resetting. You can think of other kinds of resetting, which I'll touch upon later, and it still kind of works. It's just a little bit more complicated. Okay, so far so good. So then with these classical results, just as I said, you can look them up. This is the Laplace transform of the survival probability without resetting. You can substitute that into the expression I had on the previous page, and you get this. And what is alpha here is just this. Turns out it's r plus s over d to the square root. Then there's a general result that this Laplace transform, if you put s equals 0, you get the mean time to absorption. So that's quite a general result, and to see it, the mean, or MFPT is mean first passage time. It's equivalent to mean time to absorption, which is more appropriate in this case. And so this is the minus to q by dt. Q is survival probability. D by dt is the rate of absorption, or minus that. So it's the rate of absorption at time t multiplied by t integrated gives you the mean time to absorption, and then you just integrate by parts, and this becomes, in fact, this Laplace transform when s equals 0. So simply put s equals 0 in here, and we've got this expression. So that really didn't take too long, and that's, I think, the fastest way of getting to the result. So then we've got our expressions. Remember, what we're talking about is diffusion with resetting. The mean time to absorption by a target at the origin is this. And if you simply plot this, what you'll see is that it diverges when r goes to 0. And so that corresponds to the result that without resetting, the mean time to absorption is always infinity. It also diverges when r becomes large. And that's easy to understand. If you're resetting too much, you don't let the particle get anywhere because you're continually resetting it. And so, again, the time to find the target at the origin diverges. And in more detail, there's a unique minimum in between. If you minimize this with respect to R, you get a nice equation in terms of gamma. So gamma will come up later. So it's actually a ratio of two lengths. So there's x naught, and that's the distance to the target. And then it's divided by d over r to the half. And that's like a diffusive length, the typical distance that you travel, the typical displacement between resets. And so that ratio, the optimal value of that ratio is 1.59. Okay, so far so good. I'd just like to digress again a little bit. There's some nice results by Shlomi Ruveni and Arnab Pal, who are here. And this is sort of more generally, it turns out that at the optimal resetting rate, if you look at the statistics of the time to absorption, this statistic is the coefficient of variation that kind of measures the fluctuations in some way. And it turns out at R star, this coefficient is 1. And then you can deduce that, so if for your process without resetting, if that coefficient is greater than 1, then you can improve things by resetting. So in the case of diffusion, without resetting, the coefficient is actually infinity. But you could have other more marginal cases. And so if this coefficient of variation of the time to absorption is greater than 1, then you can do better by resetting. And that again comes back to this idea of cutting off the long tails in the distribution. Right. Now, okay. Yeah. So this is another slight digression. So far, I've discussed Poissonian resetting with a constant rate. And what I've said is that actually for Poissonian resetting, the waiting time distribution, so let's call that psi of t to the next resetting event, is actually given by this. Again, it's exponential. So instead of defining things by rates, etc., you could just define things by the waiting time and sort of think of different resetting strategies where you have different waiting time distributions. And an obvious one is a deterministic strategy where you have a fixed waiting time between resets. So it's a fixed periodic reset with time tr. And you can ask, like, which is better? Or in what situation is stochastic resetting better than deterministic resetting? So for a long time there was, so that's the question, what is the optimal choice of this psi to minimize time to find target? And actually that's not a well enough posed question. You have to say, well, how much do I know about where the target is? And there was a result. So the answer actually depends on what I'll call the target distribution. So there is a result that, okay, I think we first conjectured in 2016 with Arnab and Anupam, and the cleanest proof came 2018 with Chechkin and Sokolov. And so what they say is that basically if you know the distance, so this is the x naught that appeared earlier, if you know the distance from the reset position to the target, then you're best to choose a deterministic reset with an appropriately tuned period. And so initially that seemed like a disappointing result because it's sort of appealing that stochastic resetting should be useful somehow. But then if you think about it, that's a very artificial problem. You don't know where the target is, but you know the distance to the target. So if you're in one dimension, it's either over there or it's over there. And if you're in two dimensions, it's on a circle. So it's a kind of artificial problem. But it shows in principle that you can tune the deterministic reset. However, recently we think we made some progress. Unfortunately, we haven't written it up yet, so I didn't want to talk about it here too much. But with Shomrita Ray, who's a research fellow in Edinburgh, we found a way of, considering the problem of a target distribution. So instead of like knowing the distance to the target, you know where the target is likely to be, and then it's going to be distributed around it with some distribution. So it won't be exactly where the target's meant to be, but it should be somewhere near. And so you have some distribution that decays as you go away from the target. And in the case where that target distribution is itself exponential, then you can show that the optimal choice of psi is Poissonian resetting. So in the case where you have a target distribution, then in fact stochastic resetting is the best strategy. Yeah.
But does it depend on the amount of uncertainty about the target?
Yes, absolutely. So the question, Joachim's question was, does that result depend on the amount of uncertainty? So in that particular case, if you have if the target distribution so it's centered around x naught, so this is T, the target distribution, centered around x naught, which is, you know, our resetting position. If this is e exponential minus b magnitude of x minus x naught, then you should choose your resetting rate to, there's a formula. You'll get it as basically, what you want is alpha naught equals r over d to the half should be equal to b over 2. So it's sort of non-trivial. And what it means is that, okay, I'm getting away from the main theme, that if you like, the steady state distribution generated by the resetting is the square root of the target distribution. And that's actually the optimal way to sample it. So it's more complicated, there's different results. But anyway, I thought I'd mention that to sort of stress that there is some value in stochastic resetting. Right, so let's get on now to the cost of resetting. So as I said, resetting shouldn't be instantaneous or free. There's got to be some cost involved. So costs you can think of are, well, the first cost that were actually imposed, people didn't really think of it as cost. It was more like a time penalty. So actually, I believe this paper involving Shlomi Ruveni was the first to sort of have it's like when you reset, then nothing happens for a while. You have to sort of pay a time penalty. And Satya Majumdar and I, we wrote sort of an extensive study of this, but we were thinking of it in like a refractory period. So that's sort of when neurons fire, they have a certain period where they can't do anything afterwards. They have to recover. So we're thinking it was like a recovery period. So that's like a fixed time penalty for each reset. Then more recently, Arnab and co-workers, and also Sokolov and Bodrova, have considered, okay, like a phase where you have to get back from when you reset, you have to kind of drive back to your resetting position. And the natural thing is to think of that as a constant velocity. So then the time to get back depends on the distance you are away. But actually they thought also of accelerating so that the time to get back is a quadratic in the distance. And then you can actually, what we are doing is to go and think of we can think of the cost being any function of the distance. But I'm getting ahead of myself. So also in these papers, they considered, I should say these papers here are both experimental papers. So experimentally, to realize resetting, you need to switch on quite a stiff potential you have some colloid particle that is drifting off, and then when you switch on this confining potential, that will obviously cost some electricity, and that will eventually bring the colloid particle back. So there's actually an energetic cost to imposing that potential. And then, I should say, I should have said there's two other talks on the general theme of the cost of resetting. So Arnab will tell us about some of his works here, and Supriya might, I think, tell us about thermodynamic cost of resetting. So there is more subtle, so there's an expert there. I just mentioned that in what I'm going to talk about, the quadratic cost is relevant to thermodynamic entropic cost, or entropy production cost of resetting. So you can think of all these things. And we're trying to make a sort of general formalism where we just say that the total cost of a trajectory, So again, I'm thinking of a diffusive process here, and this is the resetting to x naught, and this is the target at 0. So we know even without resetting, we're going to get absorbed with probability 1. So there's always going to be a TF for each trajectory. And then, but the number of resets is a random variable, right? And we'll say for a given trajectory, there's n resets. And then for each reset, so the total costs of the trajectory, the resetting cost is big C, and it's a sum over little c from each reset, and there's n of them. And this little ci, so that's for reset I, it's just a function of the distance you have to reset, which is xi, the position just before the reset, minus x naught. Okay, so it's simple. The notation makes it look a little bit heavy, but it's actually very straightforward. And so as I've said, if you have ci a constant, so this function is a constant, it's like a fixed time penalty for resetting or refractory period. If we have this formula, that's like the return phase at constant velocity or constant speed v. And we can consider other cases as well. So here I'm going to, I wanted to take you through this calculation because, again, it's remarkably straightforward. So what we want to do is to calculate the joint probability of the number of resets, call it n, the first passage time tf, and the total cost. That should be summed from I equals 1 to n. So there's a lot of information there. So you think it's a difficult quantity to calculate, but it's remarkably straightforward. And this time we use again, a renewal approach, but this time it's first renewal. So because we've said there's n resets, and n is greater than 1, there's always going to be a reset. So let's make it let's consider the first reset, and we integrate over the time 0 to tf for the first reset. And remember that to have no resets, or to have the first reset at time t1 is given, the probability is re to the minus rt1 dt1. Then at that reset, we have to integrate over the possible positions of the particle. So we've got, in that initial period, there's been no resetting. So there's the Q naught there is the survival probability, and we've got the final position in there. And then it gets reset, so then we have to, well, to get to n resets, we've got n minus 1 left, and we've got time tf minus t1 left, and the cost, that reset has cost c1, so we've got c minus c1 left to spend. And we have to just make sure that c1 isn't bigger than the total cost c. Are you with me? So again, it's sort of easy, once you get the hang of it, they're easy to write down. And the initial condition is quite straightforward. If if n equals 0, no resets, then that probability, this is the probability of no resets, and then it's the f0 is the first passage time in the absence of resetting, and the total cost has to be 0 if there's no resets. So that's our initial condition. And the way to solve for this, it's again, we just use Laplace transform. Here this time we need 2 Laplace transforms because we've got 2 variables, c and tf. So we've got a double Laplace transform. We just turn the handle. It's not too difficult, but I'll just give you the answer. And so the Laplace transform of that joint distribution is simply this, where that w is itself a kind of Laplace transform of the propagator without resetting. So that's where it gets a little bit complicated, and that's where John Sunil comes in, and he's very good at calculating these integrals, and you can calculate this w for all kinds of cost functions. There's a lot you can recover. Remember, this is the joint probability of n, c, and tf. So one simple thing, if I put p and s equals 0, so that's instead of, the Laplace transforms just become integrating out the cost, integrating out the tf, and we're just left with the probability of n resets. And it turns out to be a geometric distribution, and I'll use that later. And then if I just put s equals 0 and I sum over n, I get the generating function for the cost. But there's plenty more possibilities that could be explored, various joint correlations. and moments. But in this talk, I'll just concentrate on this will generate the moments of the cost, and in particular, I'll be looking at the mean. 15, okay. Okay. So, assuming we can do the calculation, let's consider some cases. So what I'm plotting here is the mean total cost, so that's the mean big C, against, remember, gamma was that dimensionalized or non-dimensionalized resetting rate. So gamma is basically proportional to r to the half. So unfortunately in this plot, I don't know what happened, but the constant case, which is the simplest case, isn't there. But you can imagine it. It's basically, for no resetting, if the cost per reset is constant, no resetting, the average mean cost is 0, and then it sort of increases as you increase the resetting rate, which is what you'd expect. Then if we consider the linear case, so this is like the constant speed return, that looks, so that's the purple one, that looks similar, but there is something slightly odd, that the limit at 0 resetting rate, the cost is not 0, which seems very strange, because you would say no resetting, how can there be a cost? But remember, that's a limit, and I'll come into that in a moment. Then even more weird, if I have a power law, so let's say if I took beta equals 2, so the cost is quadratic, then so that's the green one, then as the resetting rate goes to 0, the cost diverges, which is even weirder, that you think, well, there's no resetting, how can there be infinite cost? But we'll see in a moment. And finally, for exponential resetting rate, and we were interested in exponential because that's sort of like a case where the cost is increasing very strongly. So it's almost like physically there's some barrier to resetting if you go too far, go beyond a certain scale. And in that case, then the mean cost diverges at a finite resetting rate. So why should we get this divergence when r is small? So this is the slide I was actually referring to that's a bit detailed and doesn't look very nice. But so if you have some queries here, please ask. So this will explain, hopefully in a simple way, why we get these strange results in the small r limit. So as r goes to 0, remember I had a geometric distribution for the number of resets, and it actually just becomes simple, that it becomes, when r goes to 0, it becomes 1 minus gamma to the n, where gamma, remember, is this, and alpha naught is r over d to the half. So we had those two things before, but you have to sort of remember those definitions, that gamma is proportional to r to the half and x naught. So basically when gamma goes to 0, so p of 0 is basically 1 minus gamma, and the probability that there's one reset is gamma. So there will be the dominant cases. Then we consider the approximate position at a reset. So this is an approximation. We're just saying, right, the particle, forget the absorbing boundary. We've got a diffusive particle, so that's the distribution after time t. And we want the probability of the time just before a reset. So then we need to average over t being the time of the first reset. So this, if you think about it, it's just giving you the average position just before a reset. And this integral is sort of one that's in Gradstein, and it's a well-known one, and it's simply this, which might seem surprising, that combination actually gives you an exponential distribution, much like I've drawn there. So then, at the reset, the position is this exponential distribution. So if I average, let's say, x minus x naught to the some power beta, then this will, it's just going to be, the answer will be replacing this by 1 over alpha naught, and alpha naught is proportional to gamma. So this will simply scale like 1 over gamma to the beta minus beta. So basically the average, so when r goes to 0, the average cost of a reset is going to be gamma to the minus beta, so that's going to diverge. And so when we calculate the average total cost, it's going to be the combination of one reset times this cost will give us gamma to the 1 minus beta. And that turns out to, that agrees with the exact result. So that's how you get, in the limit r goes to 0, you get a cost. So if beta equals 1, which is the linear case, this is just a finite, the mean cost is some finite constant. If beta equals 2, then this is divergence. So that explains that surprising result. Okay, let me hurry up. The other thing we can consider is, so far I just considered the mean cost. We can add to that the mean time to absorption. So if you think of, so now we're thinking of the cost as a time penalty. So we would have to normalize the cost appropriately to give it the right dimensions. But we just think of the total completion time being that this cost plus the usual time to be absorbed. And so what we want to do, so we want to sort of minimize this with respect to R, to find the resetting rate which minimizes this total completion time. And interestingly, so if beta is, so remember beta 0 is a constant cost of a reset. And in that case, actually, to minimize everything, you just would set R equals 0, or R goes to 0. And then for, that holds up to beta equals 1, which is the linear cost. Then for beta equals 2, the actual optimal value of R turns out to be, the dotted line there is the value in the absence of a cost. So strangely, for beta equals 2, it turns out that having this quadratic cost made absolutely no difference to the optimal value of R. It's just exactly the same as as in the case where you have no cost. And then if you have beta, so the cost is increasing more steeply than quadratic, your actual optimal resetting rate is increased. And the reason is up here, so the optimal resetting rate is increased because the cost for large resets becomes exorbitant, and so you want to reduce the chance of having to reset a long way, so you have more resets. And so the optimal resetting value is increased. And here, it's just for the quadratic case, it turns out that the average cost of the resets has exactly the same form as the mean time to absorption. So minimizing them, you get the same value. And so you get this nice plot. I think from people's faces, I lost people there. And I'll summarize at the end. But okay, actually, I can summarize here. So for when it's the cost per reset is constant or linear in the distance, then the optimal R is basically, it's the limit R goes to 0. But if it's quadratic, then the optimal R is unchanged over the case where there's no cost. And strangely, if beta is greater than 2, then the optimal R is actually increased. You're best to have more resetting to avoid costly resets. Okay, finally, this is just briefly the exponential one. There is an interesting thing that happens. I don't have time to go through all the details. But if you can do an exact asymptotic calculation. We have the generating function for the cost. You can work out the large C behavior of that distribution. And in fact, it's a power law. And that seems at first a little bit strange, because where does the power law come from? And it's actually, okay, so the cost is exponential. And remember, we saw that the position distribution at the first reset is exponential. So basically, you have these two exponentials. If you write them in terms of each other, you get a power law. And that sort of comes out. You also see that in the trap model in glass sea dynamics. So that you get a power law from two exponentials. And one interesting consequence is that we have a power law. So the cost, I don't go through the details, the cost per reset has this power law. And that's exactly the same form as the total cost. And what that means is that one of for these large cost events, is like one of the resets is making all the cost. And we call that type of phenomenon condensation, where you have this bunch of random variables, the cost of the resets. One of them is dominating the total cost. Okay, I think I've said enough. So to summarize now, so what we've studied is an additive cost of resetting, so just simply a sum of, a cost for each reset, and the cost is just a function of the distance. And we considered constant linear, parallel, exponential cases. And there's various optimization problems that we've looked at, minimizing the mean total cost and minimizing the mean completion time. And this, I think, was sort of, for me, this is the most general result, that your optimal resetting rate may be decreased, as you'd expect, but it can also be increased by having a cost. So, and that the increase is simply to avoid very, very costly resetting events. You end up resetting more to avoid those events. Yeah, and I think that's all I wanted to say. Thank you.
Thank you, Martin. Questions? I actually had a question.
Please, go ahead.
Go ahead first.
You talked about the small gamma limit. What about the high gamma?
Oh, hi, Gamma.
For different values of beta, do they diverge in the same way?
Actually, that's a good question. So here's the relevant plot. So you're interested in what happens out here. So clearly, yeah, you get a divergence. We didn't actually explicitly analyze that. I just assumed, I think, that it would diverge if you take the resetting rate to infinity because you have so many resets. Didn't actually analyze those limits.
Yeah, thank you, Martin. So as you discussed, this R goes to 0 limit is a bit singular. I mean, it's not, doesn't coincide with R equals 0 strictly. So there must be some kind of boundary layer, no? I mean, boundary layer in the sense that you get something singular because you get some kind of large T limit. No, what I'm saying is that, yeah, so I just would like to understand why this, I mean, I have hard time to understand that this R goes to 0 in the sense it's different from the R equals 0 strictly. So there must be a time scale there that.
I don't know. I don't know if
don't
okay,
think
the
so?
explanation, so if you look at this is perfectly smooth, but you can't approach it from that side.
Yeah.
And so there's a discontinuity, if you like, as you approach R goes to 0 and R equals 0. And yeah.
I guess if you would look at your system up to time t, say.
Say that again.
If you look at your system up to time t and define the cost of resetting up to time t, so in a kind of average cost, 1 over t times the integral from 0 to t, then there will be a crossover, right? So probably for RT fixed, and there should be a crossover, and what?
Okay.
So early time behavior should be smooth,
Yeah.
equal to 0 and
Yes.
then crossover to.
Yeah, I guess so. Yeah.
Yeah. Okay. That's
Okay.
a good suggestion.
Yeah, there has to be a scaling function connected.
You speak into the mics. I
No,
think.
I'm saying that there should be a scaling function connecting the two limits,
Yes.
basically.
So you were discussing why it's like constant in the R equal to. Oh, in the R equal, yeah. Actually, about the fact that it's constant, like you have a cost even when you have R going to 0.
Yes.
Is it something? Could it be something like this, that if you're not resetting, the system has a chance to get quite far away, and then there's a bigger cost for it to be put back again.
Okay.
So there is some kind of compromise between letting it wander too far and then like paying a high cost to reset then at the end of it. So.
I think it is. So in most trajectories, there's no resets, so no cost. And then there's an occasional one there where there is a reset, and that incurs a very large cost.
Exactly.
That generates a finite.
Yeah, so something like that.
I don't have a deeper explanation than that. I mean, maybe one should try and formulate it more mathematically.
Other questions?
So I want to ask that, so you need minimum, I mean the number of resets that should be an integer number.
Yes.
So, like, you are doing no reset and you are doing at least one reset. So this number of some gamma goes to 0. So gamma is somehow connected to R, or
Yeah.
the reset rate. So
Yeah.
is there some limit, like gamma cannot be 0, but it should be some number because the number of reset is minimum 1. So from going to
Oh, the resets are integer, so it's.
So it's like gamma cannot be go to arbitrarily low value.
Yeah, I don't know. I'm just repeating myself. I think of it as a limit. So R and gamma are positive. We're taking the limit that they go to 0, and that has a well-defined limit. That is not the same as trying to come the other way. So you have a discontinuity or some singularity at R equals 0. I don't have a more sophisticated way of thinking of it than that.
Okay, so maybe we should thank Martin again.
Can you hear me from back? Yeah, okay.
Okay, so now we have Arnab who will tell us a little bit more about beyond classical reset.
Thanks, Rupiah. And thank you, Sanjeev and Manju, for putting up this meeting. So I have also, it's great to be back actually at RRI, because from here I did my PhD. And also I have a very, long connection with RRI and also resetting, because as Martin mentioned, right, so they wrote the paper together at TIF perhaps in 2011. But I think during that time he also visited us and gave a board talk on resetting, even probably before putting the paper on archive. So, this paper for a long time. Okay, so given that there have been several talks actually on resetting, everybody has given some sort of introduction. I think we don't need that much. Still, let me just rushing through some of this. So, we have heard about search processes and how it helps under resetting. Then there are these algorithms. But I just want to mention that the concept of resetting is not really just qualitative anecdotes, but also they could be of real use, or they are being appearing in different natural settings. One is this chemical reaction where an enzyme reversibly binds with a substrate to form an intermediate state, and from there, there are two options. Usually, this unbinding event is what we connect it to resetting. There is also this very nice connection with the protein-DNA interaction. So, these are some seminal works by Berg and then Slutsky, Mirny and all. So there is this protein which actually tries to find this target site along a long DNA. And there has been experiments by Reeds on lac repressor and other proteins. And then eventually it has been understood that the protein actually mixes between two different types of motion. One is the simple diffusion, and one is when it relocates from one plane to another plane. And so when it moves from one plane to the another plane, or maybe coming back to the same plane after doing the relocation, it restarts its search. So it's like restarting its search, finding the target again. And more to this, recently you also realized that this resetting also naturally appears in this connection with this protein coagulation. So what you are seeing here, you have this misfolded protein. Not really it's usually the thing is it's an unfolded protein which is in a higher temperature. And what it does, it has to find this native state, which is where the protein wants to reach. It's a long molecule. And once in a while, what can happen that it actually can reach to this misfolded state. Okay, this is something which people It's very well known in the chemistry, biochemistry literature. So then what happens, there are these chaperone molecules which actually come, they're engineered in such a way that they come and actually help the misfolded protein to go back to this unfolded state again. Okay. Of course, there might be some time involved, etc., etc. I'm not getting into the details. And of course, there is also energetic cost to this. These are like biochemistry. But then the role of the chaperone here essentially is to take the protein from this metastable state, which is where it was stuck, and then take it to the unfolded state again, from where it can, restart to go back to the native state. So like as we have understood that it's often going back to the going to the scratch is essentially sometimes really helps. So the plan for today is I really would like to give a very brief summary of the first passage under instantaneous resetting. And then I would like to talk about this non-instantaneous resetting, how it can be applied to generic home range search processes and experiments. And I would like to touch upon the synergetic cost of resetting, which will have a very strong overlap with Martin's talk. And at the end, I would like to discuss about something which we did very recently. Okay, so a very elementary exercise with resetting, although it's very pedagogic. So let's say that you have a ballistic particle which tries to find a target which is at distant cell, and then what you are trying to do, so you have the L by V. There is no stochasticity in this process, and what you have, you take the same process, but then you apply the resetting. So there is a resetting clock. When it happens, you take the particle, put it back. So there is a ballistic particle which you are sort of like hindering its motion. If you do this, so of course, the T will be greater than L by V. So resetting a ballistic motion is not going to be useful. But on the other hand, let's take this, the seminal work by Martin and Satya. So where they looked into this process, where I have a diffusing particle, you have a target, and then you are resetting the particle with a rate R, and you are interested in the time it takes for this particle eventually to reach the target. So when you do this, if you just plot this guy as a function of resetting rate, so you are not surprised by these two limits. So the R going to zero limit is the classic Brownian motion, where it is infinite due to Levy. And also, when you have very high resetting rate, you are not just allowing the particle to move farther, right? So, but in between, what you see is this very nice result about that you can render this mean first passage time finite. And of course, there are more details, like you can also find an optimal resetting rate. So Martin discussed already all these things. Okay, so I will rather take a slightly different approach to this problem than what Martin already did. So Martin and Satya already explained, showed us a general formalism where things were written in terms of probability distribution or survival probability. So instead of that, what I'm going to do, the approach is I'm going to write a renewal equation in terms of the random variable itself, okay, instead of writing for the probability or the survival probability. So what we do is that you have a recurrent process, you have a trajectory, so the trajectory can hit the target at some point of time. This is a process completion 1, another time, but then you could also have resetting, so you go back to the initial position, from there the process restarts and keeps on happening. So if you look into this, you have many possible events. So, and I'm interested in the total time of this compound process. So one component is when you did not have any resetting. So this is the first component. So TR is the total time. If it goes as T, given that you reached before any resetting actually had happened. Otherwise, you go back, you had this time penalty, which is the resetting time itself. You go back to the origin, and from there, the search process restarts, right? So then this is actually IID copy of this guy over there for this particular condition. And now we have this very simple renewal equation in terms of the random variable, and you can try to calculate the moments and also, in fact, moment generative function and other quantities. So yeah, so this is rather simple, and then I just want to give you the result. So effectively, this mean first passage time, it looks like minimum of, it has two components, like a numerator has this guy which is minimum of 2 random variables, and then there's a probability that T less than R. So just want to emphasize one part here, So far I have not really specified what is the, what is the kind of resetting I'm taking, whether it's an exponential or something else. Neither I have anyway specified what kind of stochastic process I'm looking at, whether it's a diffusion or not. More to this, let's say somebody is doing an like a computer simulation and doesn't really have any access to exact form of probability distribution for T or R. So in this case, you have, let's say, like data for T and R, and you can actually try to numerically compute both the numerator and denominator. Okay, so this is, I think I just wanted to, add this advantage of using this kind of approach. Of course, now when you have resetting which occurs with the rate R, so you get this guy. This is something which also Martin mentioned in a slightly, it was written slightly bit on a different way, but this is effectively the thing. So you have this, the underlying first passage process has this first passage time distribution f of t. If you take the Laplace transform of this and then plug in this expression, you get back for the classical result what Martin and Satya derived some time back. Okay.
Can you find higher moments also?
You can actually calculate the higher moments, and as a matter of fact, from here you can calculate the moment generative function itself. Okay, so there is something called resetting transition. I would like to walk you through that. So the question is, when does resetting help, right? So a generic understanding for diffusive search is that resetting is always going to be useful. But for any arbitrary stochastic process, which let's say already has a finite mean search time, what can you say about that? Can you say like when resetting is going to be useful, right? So to understand that, what we can do is we can take the expression we had before and do a very small perturbative expansion for small r, okay? And assume that, of course, as I said, that it has an underlying mean time which is finite, and ask this question. So as you can see that if this term is negative, at least in the linear order, so this will be smaller than this one, right? So we can just rewrite this guy together, and then what we get is something called a CV. It's a statistical dispersion known in the literature very well. So it's a ratio between the standard deviation of the underlying process and the mean of this. So if this is greater than unity, you are sort of guaranteed that resetting is going to be beneficial, at least for processes which have a well-defined mean. So it seems that CV equal to 1 is a sharp boundary for this kind of transition. And CV greater than 1 actually guarantees for an optimal resetting rate, right? Because you started from some finite time, then you applied resetting, it was helpful, so you will have at least one minimum, so that will correspond to an optimal resetting rate. So from there, you can sort of intuitively think about this particular phase diagram. So you have this optimal resetting rate. So if you plot with respect to CV over here, and as you probably have noticed, the CV, if you see to understand the effect of resetting, actually you need to look into the qualities, the quantities of the underlying process. So this, if I plot it over here, so CV equals to 1, beyond which resetting, there is an optimal resetting rate which is finite. So this is what I call some sort of a transition, resetting transition. Okay, so this has been put up again and again. So what does actually CV greater than 1 mean, right? So like what CV, essentially this tells us that how broad a distribution is. Essentially, if you're looking at the first passage time distribution for the underlying process, how broad this distribution is. So for example, when we were looking at this ballistic process, right, it is because there is no stochasticity, right? So it has a CV which is almost close to 0, right? So there is, we understood that resetting is not going to be useful. But as you increase CV, and then you have this marginally dispersed, which is basically the boundary. And if you go even further, so you have broadly dispersed distributions, and then if you go further, which is basically the diffusion regime eventually, okay? So this essentially summarizes, like when resetting works, etc. And physically, if you want to understand what actually broad distribution means, this can come from different kind of physical scenarios. For example, it could come from, for simple diffusive systems, like you could have detrimental pathways, basically the trajectories which are going very far from the target. But if you are also looking into the a diffusive search or some other kind of search, let's say in glassy dynamics, or some people use it also in algorithm setups, you could have deep kinetic traps, large barriers, bottlenecks. This can give rise to a very broad distribution for the underlying fast passage. And also in chemical reactions, a very natural way actually to generate a broad distribution is if you create parallel pathways. And so if you think about chemical networks, they have parallel pathways, and in each path there is a certain probability to go. And it is not guaranteed that in each path what is the rate, corresponding rate. So you could have a very strong bias between different paths, which could lead to a very high, very broad distribution for the catalysis time. So in all these scenarios, whenever you have a natural scenarios like this, if you apply resetting, it's always going to be useful. Okay, so there is something, we try to emphasize all these things in this paper, and there is a very recent review we wrote here, and where we again try to put up all the physical context which at least we understand. Okay, so I'm going to probably rush through this. So is the CV criteria sufficient? Okay. So CV greater than 1, of course, guarantees that there is an optimal resetting, but is it sufficient? So I'm not going to give the details, but you can work it out a very simple example where you have, let's say, 2 absorbing boundary, and then you have a Brownian particle, which is trying to go to one of the boundaries with a certain velocity v. If you look at the mean first passage time of this problem, so you're used to seeing this kind of plot, right, where if you change the resetting rate, this is a shifted mean first passage time. You see that in this case, resetting was not useful, but in this case, there is an optimal resetting rate. So you see this kind of plot, which is intuitive. But then also, on the other hand, when you change some parameters in the system, you suddenly start seeing this kind of plot. Okay, so the mean first passage time has this particular kind of form. In particular, note that in this case, you have an optimal resetting rate, which is over here. But as you change the parameter here being the initial condition, actually, the position of the particle, x0, you see the optimal rate actually is in both the places, and then it switches to 0. So this is something what Dennis showed in his talk. So it seems that even if you have CV less than 1, as you can see in this case, right? So CV is less than 1, but then it went down. So initially it goes up, which essentially tells the slope is less than 1. So it goes up, but then it comes down later. Okay, and in this kind of cases, so you should not infer that CV criteria is necessary, but it is sufficient enough. And in such cases, at least for this case, what you can see that optimal resetting rate with the function of system parameters, whatever system parameters you are tuning, with that it has some sort of a continuous transition. But then in this case, as you see that there is this optimal resetting, it has actually a jump. So it has some sort of a discontinuous transition. And again, a disclaimer is...
What is that PE?
This is the Peclet number. Because you have a velocity here, okay, so you can assign a Peclet number. Yeah, sorry, I should have mentioned. Yeah. So, of course, this is not really, as I said, it's not really a phase transition or something like that, thermodynamical transition. This is just a behavioral transition. When is resetting useful and when it is not. Okay, and then you can also show these kind of things not only for diffusive system, but also for chemical reactions and other things. Okay, so there is an interim summary for this part, is that resetting can expedite completion of many arbitrary stochastic processes, and then resetting also should not be considered as a default operational protocol, because you could have different kind of scenarios depending on what kind of system you are looking at, what is the underlying first passage time distribution and things like that. So again, this, I would like to point out this review, which was written by Martin, Satya, and Gregory. Had almost all the things for the last 10 years, and recently we tried to write also a much shorter, concise review on the effect of resetting on first passage. Okay, so towards practical resetting, so I think this video will not work, so I just go out and then come in again. So we, let's see. Yeah, okay. So this is an experiment which was done in EIS group from Tel Aviv. So what we see here, you have a silica particle, micron size, and then the particle is diffusing in a water. And then we already have a MATLAB code written for exponential resetting times. So whenever this time comes, what you do is you basically project an optical trap on this particle. You let the trap hold the particle and bring it back to its origin, okay, to the center, which is some fixed point. Okay, so this, let's say that hopefully this will work this time. So as you can see that it diffuses, and then you have some random time. You project the trap on the particle and bring it back all the way. And also important is you must hold the particle all along when you are coming back. So of course this basically tells us that like resetting is not really an instantaneous physical setup, right? So if you want to actually experience resetting in a real system, you probably have to come up with slightly smarter protocols, and which might cost a certain time. And also I would like to mention this paper by where Satya and Sergio, they were together. They slightly used a different protocol, and that was involving certain trap. I will also come to that in a slightly different context. Okay, so what are the key observations from the experiment? So as I said, like this is the typical trajectory. So it diffuses, and then you have this clock, these time scales, which are basically written in an array. It fed to MATLAB, and then it fed to the holographic optical tweezer, so that it comes back to the center. And when it comes back to the center, you see that there is a waiting time. This is something which Satya was mentioning as an equilibration time. So this is a very sharp width for this distribution. When the particle comes, it needs certain time to equilibrate, which is also shown here. But the take-home message from here is that it's a finite time physical process, because you are returning it with either certain velocity or by some other means. Also, another thing is it's a spatio-temporal process. What I mean by this is, if you go further, it will take more time for you to return. So the space and time in certain way, they are actually coupled. Okay. So and also, as I mentioned, there could be different type of return protocols. So you could have a constant velocity return, then you could have a constant time return, which Martin mentioned. You could also have different type of return protocol. You could have a space-dependent velocity, and also other things. These are usually what we call deterministic return, because when you are returning, there is no stochasticity. Okay. But then also you could have something called stochastic return. So what is a stochastic return is that this is somewhat similar to what the experiment by Satya and Sergio. So what is happening here is that you have a particle which is diffusing, right? And at the resetting time, you switch on a trap which is centered at the origin, okay, which is the resetting location. And so what the particle, it is somewhere here, right? So it sees the potential which has a minimum at the center. So it feels a potential gradient, right? So it comes back, but it comes back stochastically this time, right? So this is what I mean by stochastic return. If I understand correctly, so in the case of their experiment, what they did is they maneuvered this part as a very fast process, so that eventually you can say that this is actually zero. But generically, you can think about a more generic process where all these things have to be put together. So this part was done by when I was finishing my postdoc, and this part basically with Anupam and Deepak and some other guys. Okay, I don't want to really don't want to go into the details. I just want to emphasize one part, that if you want to actually understand this process, you need to think about this is a compound process which actually has two components, right? One is a search phase, one is a return phase. So if you want to write you want to understand the position distribution of the particle, you need to actually decompose into two parts. One is this motion phase, one is this return phase. And you need to, then of course you can write the time-dependent probabilities for each part, but skipping the details, the effective idea is that you need to write Fokker-Planck equations or master equations for each one of the phases, okay? And then you have to join them at the boundary with some boundary conditions. So just saying, this is, sorry for this, this slide. So you see that this is the instantaneous resetting when you had, you could have some generic operator for some stochastic process, but these two terms remain the same. One is this, we already know these terms, but then when you have the motion phase density, what you see that exactly at the resetting time, the particle is switching from motion phase to the return phase. So that is basically the lost term. But then when the return phase, when the particle actually comes back to the origin, so then it switches to the return phase again, to the diffusive phase again. So there is actually a gain exactly at the origin. Okay, so this is somewhat a bit more convoluted, and then you have to solve this coupled equation. And there are also other approaches. So this particular approach is specifically for Poissonian resetting. And then there were also other approaches by Anna Bodrova and Igor Sokolov using a slightly different approach, yes. And I think they can also extend it for different type of resetting protocols. Okay, so I just wanted to mention that you can actually use this formulation. This is from the experiment. So this is the radial distribution. And you can see that this formalism essentially fits with the data. These are data points from the experiment. Okay, and now going to the first passage aspect, which has been the central focus for my talk. So this finite return time, of course, aside from this experimental aspect, also, there is this generic ecological approach, motivation for this one. So, for example, as Darwin mentioned at some point in his book, that it may be remarked that most animals and plants keep to their proper homes and do not necessarily wander about. And we see this with migratory birds and animals which return to the same spot. And this is an experiment, ecological experiment, which was done in Scotland. And what you see is these birds, it's called sea gannets or something like that. So these are basically the largest, largest breeding ground or something like that. So they go out and then they come back to this home, so to speak. So the generic idea is that if you are thinking about this resetting with a finite return, so you can think about it as a home range search process. Okay, so home being the reset where you actually reset. So let me try to emphasize a bit more on this. So just take a look into this butterfly, which doesn't really have a permanent dwelling. So it essentially goes from, just roams around till it finds a particular flower, and then the search is over. On the other hand, if you think about a bumblebee, so it actually has a home. In some sense, it's called hive. So then what happens is it goes out to find the flower, but if it doesn't find, so it can actually come back to its hive and then restart its search. So this is more or less the general motivation we have for the home range search. So this is, as we understand, this is actually a cyclic process. So it has these three phases: search phase, if unsuccessful, then return. This return could be different type of returns. And then, of course, there is a waiting time at the home. So we can again try to write a renewal equation, that the same renewal equation we wrote for the random variable itself. And what I understood over the years, that this actually makes life somewhat simplified, at least for me. So you have these two components. As I said, if it finds it successfully, the game is over. Otherwise, there is a resetting time. Then there is a return time. Then wait. But the most important part here is this tau of x, which is basically the return time. So as you see this tau of x, it depends on from where it is starting to return. So as you can see that it's starting from this place, it's x1. If it is starting from here, it's x2. So this is exactly similar to what Martin defined as a cost function. So which also dependent on mod x minus x naught. So this is something which you can do, and then the question is when is the home return beneficial, in the sense resetting is beneficial. And of course, this has a lot of implication, because you can now use this approach to experiments and also other many different kind of things. So let me not get into this technical details, but I just want to mention that when you calculate the mean time for this entire process, this actually has three components. One component is basically the search phase component. Then there is a return phase component, and then there is this home phase component. So as you can see that this is actually what somewhat Martin showed. He has this C function over here. So what it essentially means, let me try to explain. So you have a particle which is diffusing, and let's say that exactly at the resetting time it's somewhere here at x, okay? But then if the particle has to be found without being absorbed, you actually have to integrate it with a correct measure. So this is something you can do. And of course, you also have to, this is the time when the resetting occurred, so you have to also integrate out this resetting time with certain distribution. And as you can see, I'm not really specifying what kind of distribution I have chosen. So for diffusive search, as you can see that there is this classical result by Satya and Martin for the instantaneous resetting, but of course, because it's a deterministic, it's a finite time return, there must be an additional cost to that. So this is exactly that. So this is the return cost, which is being added to the total time. And also, as a similar to the classic diffusion problem, in this case, also you can show that when you return to home at finite time, so diffusive search, so the home returns are also useful for, at least for diffusive search. But then, of course, you can ask again the generic question. So let's say that you have this diffusive kind of process when you had infinite mean first passage time, and we understood that home return always wins. But then if you have finite mean first passage time, let's say in a confining domain or something like that, so the question is when, like what is the condition when this home return is going to be useful? So let me not get into the details, but let me just point out that you can again compute a criteria like the CV criteria, a very universal criteria which depends on the underlying process. And then, of course, it also depends on the return time, okay, the mean return time. So the two take-home messages from here that home returns also again can be very useful when there are large fluctuations, which we also understood for the instantaneous resetting process. And today I didn't discuss about I mostly focused on the mean time, reduction in the mean time. But you can show that if you are looking into the fluctuations, even the fluctuations also can be reduced by adding resetting. So, okay, so this, now we'd like to switch to this energetics of resetting, how I'm doing with time, 13 minute questions, okay, so let's say 10 minutes, okay, ballpark time. Okay, so this energetics of resetting again has to do with the fact that I'm actually returning in a finite time, right? So the entire point is that, let's say again go back to the experiment, so which is over here. So the particle is doing diffusion, but then you switch on the trap and let the trap bring the particle all the way back to the condition, right? The catch point here is that you actually have to make sure that the particle is inside the trap during the entire return process. So how can you do this? So the energy during the entire return process. So how can you do this? So the energy cost essentially is just proportional to the return time. Okay, and this is power, leisure power, which is fixed at 1 watts. And then this is the return time. There is no specific instruction on how you are returning, at least in this. Then what you can do, you can actually try to calculate the statistics of this time. So this is if this is tau of r. So what will be the distribution of this tau of r over many trajectories? So you can calculate this using this particular, this is the distribution. It's actually very easy to understand. This is the part, this is the resetting time distribution. This is the underlying propagator, whichever you are choosing. And then depending on what coordinate you are looking at, you have to just integrate over the entire phase space. If you do this, and especially for the velocity return, you get this energy PDF, which actually looks like something like this. But the more interesting part comes in this mean energy part. So this mean energy, as you can see, it goes proportional to v minus 1. So this essentially means that E is actually proportional to 1 over velocity. Okay, velocity meaning the velocity at which you are being returned. Okay, this is something you can exactly show. Okay, so now the question is, so it goes inversely proportional to the velocity. So it essentially means that you can actually return very fast and make the energy, like diminishing, right? You can make it slow down. But the point is, you cannot indefinitely do that. There is certain limitation, because when you bring the trap, the particle can be inside the trap up to certain limits, okay, and that it doesn't have to do anything with with the resetting experiment. It comes with the radiation theory itself and it shows that the maximum velocity using which you can actually pull the trap, keeping the particle inside, it is actually proportional to the power and the viscosity and also the stiffness of the thing. Okay, so this is something which people have already calculated in the optics. And as you can see that if you just put this maximum velocity over here, so this gives you minimum energy. Okay, and then you can put together all these guys. As we can see, this average energy actually cannot be lowered indefinitely. Okay, there is a cutoff because the velocity has actually a cutoff. Because if you want to bring the particle faster than that velocity, it will just escape. You cannot hold the particle inside the trap. So this is morely from an experimental point of view. Yes, Sanjeev.
So here, like in your energy cost calculation, it's only the laser
Yes.
DC, right? But you are not counting the energy. It also needs energy to bring the particle, right? Because there is a mechanical thing which moves the trap, right?
That is this. So this is the time it takes for the particle to return.
Okay.
This is the energy. So the power you need, the laser power, which is over here, and the time it needs for the laser to bring the particle to the origin.
But this laser power also depends on the time, no?
No, the laser power is fixed.
Because you have to keep the laser on for that much time, right?
But this, yes, so this is proportional to the tau of R, and this P is independent of tau. So the P is fixed at 1 watt, and the tau of R is essentially the time you need for the particle. And of course, we are not really specifying what kind of protocol you are choosing. Okay, so now this energetic cost of first passage, so that was like for the steady state case. But this, you can also have a success, so you can also think about putting a virtual absorbing wall in this 2D setup. So let's say that you have this particle over here which is diffusing, and then there is this absorbing wall which is over there, which is it's literally parallel to the y-axis. So you can think about projecting into this x-plane, and then it has to just cross this certain distance, and that's your first passage under resetting. So again, we are defining the work exactly in the same way, so return time. But here there's a catch is, the return time in this case also should be conditioned on the fact that you have not been absorbed, right? So this is the reason you see that this propagator here has been now from G0, which was just the free propagator, now it's the propagator in the presence of boundary target. And then this P is actually a factor which is coming from the geometric distribution. So why geometric distribution? Because you see that what is happening here, you actually have a success failure probability process, right? So you have, whenever there is first, what you want actually a successful event. That's like a first passage. But before that, you have many unsuccessful events, which is basically the resetting event. So you have failure, 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 and then there's a success. So this is essentially a geometric distribution. You can calculate the mean number of resetting events up to this first passage, and you can fit all this together in this formula. So this is the mean number of resetting events up to that, and this is this tau return, t return, which you can calculate from this guy. So again, now we come to the same conclusion which Martin had in the paper. So mean energy per first passage event, if you just take the limit, you come to this certain fixed value. But then again, when r is equal to 0, it is exactly 0. So there is a jump exactly at r is equal to 0. Okay. This is also something which we see in the experiment, and already we had a discussion on this like half an hour back, that the way at least I understand that Martin showed it slightly more general perspective, at least in this case, the average number of reset vanishes as square root of r. This diverges as 1 by square root of r. So they cancel out, but in other cases, it doesn't cancel out. But at least in this case, the way I understand is that you, at least when r is equal to 0 event, you can have at least 1 or 2 events along the entire first passage, right? And whenever that happens, so the particle wanders off. So, and then you have to bring the particle from there. So that is something I think is costing this finite energy jump. at least for r going to 0 limit, which is not there for r is equal to 0 because it's a strictly r is equal to 0 limit. But of course, like as discussed, there could be some scaling, etc., etc. So this is something which we saw in the experimental paper, but recently also we saw it in a slightly different context. For more of this stochastic thermodynamics of resetting, we also have worked a bit on this, and tomorrow also Shukriya's talk is there. So I think she will be telling us more about stochastic thermodynamics. Okay, so I think, do I have like 2-3 minutes? 5 minutes. Okay, so like this is something which something we did very recently, that we asked the questions. So now we have this non-instantaneous return protocols, and of course they are more expensive than instantaneous return protocols, right? Because it is taking certain time. So can it do better? So just to exemplify this particular case, just imagine that that setup which we discussed, that you have this particle which is diffusing, and then at the time of resetting, what you do is you actually switch on a trap. And when you switch on a trap, the idea is basically when you come to the minimum of the trap, you switch us to return phase. Now on top of this, what we say in this particular problem, that the searcher is actually not blind. Okay, so even during the return phase, it actually can detect the target. In other words, if you think about it, it's like if you have a target somewhere up here, so the particle can actually go once in a while go uphill, right, and can hit the target. Usually, because it's now not blind, so it can actually detect it. In all the previous cases, we did not have this condition. So this is something which we try to see. So I think I'm really running out of time. So this is this archive preprint we have, and then Arup, who has been leading this project. So I just wanted to emphasize probably this one, that if you look into this mean first passage time, we are used to seeing mean first passage time as a function of resetting rate, but let's say for a change, let's plot it as a function of Peclet number. So Peclet number, just imagine that the strength of the potential. Doesn't matter at this point which particular potential, but let's say that you have potential over here, potential strength over here, and this for this, and each one of these plots essentially for different z meaning the resetting rate. Okay, and the dashed line corresponds to instantaneous resetting, which is basically high Peclet number, because you see that when you have a very strong potential, so it's like you are coming back to the origin instantaneously, right? So these are the dashed lines. So if you are not surprised by these two plots, which is for z is equal to 2 and z is equal to 5, because we see that the stochastic return mean first passage time always stays above the instantaneous resetting. So it's all good. This is something which we are used to seeing. But at least for this case, as we increase the z, the resetting rate, we see for certain Peclet number, okay, so the stochastic return, actually the mean first passage time fell below the instantaneous resetting. Okay, so at least you can think about a set of Peclet number for which the mean first passage time actually worked, was like improved because of the stochastic return. And then of course then you can ask this question, you can put this question in a more general framework, like, okay, for generic process, can you say something more generic? So it seems that you can actually come up with some sort of universal relation, and this is the criteria. So this left part of this, I didn't really explain. So this essentially, this left part is, during return, you could either detect the particle, the target, or you could return to the home. So this, there is a minimum of these two guys over there. So this time essentially is entirely during the post-resetting phase, after resetting what has happened. But then on the right-hand side, you have this instantaneous resetting. So you basically need to look into the ratio of these two guys, and then only you can infer what is going to be useful. Using this generic thing, at least for diffusive search, you can actually come up with a comprehensive phase diagram. And depending on what you want, either you want an instantaneous return or beneficial for stochastic return, you can actually pick up values for Peclet and Z. So Z, as we understand, the Peclet is probably not very easy to change because it comes with a certain stiffness, But resetting rate is rather easy to maneuver, at least in experiments. So this phase diagram will give us some sort of a comprehensive way to select the parameters. Okay, so I think Arup has a poster here, so he will be able to tell us, tell whoever is interested more. So, okay, so the summary is, resetting is actually, we understand after 10, 12 years of resetting that probably we have to also slightly switch from instantaneous to at least non-instantaneous case. And then what I have tried to show that the blind returns, of course, just adds additional time penalties. But if you have some sort of a non-blind perceptive returns, then there can be some significant speed up. And then, of course, there are different type of resetting mechanism. There are different type of return protocols which are experimentally amenable. You can think about. And then general question is what happens to the optimization in this cost. So these are like some general direction. Just would like to acknowledge some of the people with whom I had the opportunity to work on resetting. And then when in doubt, you just reset. Thank you.
Questions?
So in the energy cost, there is no non-monotonicity, or
which one? So there are two energy costs I showed. One is for the first passage,
yeah,
the finite jump one.
Right.
And then there was another one.
yeah, I'm talking about the second one, I think.
Okay.
So
This one.
This one.
Yeah.
So there is no non-monotonicity.
No. It just goes down, and then it saturates to R going to infinity, which is basically the R is equal to 0.
Okay. Okay. Thanks. Yeah.
And of course, it it has exponential.
Maybe I have a short question again to this energy cost. So I can also estimate this cost by just multiplying the force times the velocity and integrating over this time, right? So that's another, like, it's work done by the trap, right?
Yeah, you could.
So will this both definition give me the similar answer, or they are equivalent or different?
Well, for at least if you have a linear potential.
I mean, you have a quadratic potential.
Quadratic
no?
potential, it
will be different, right? Because
right, yes.
it's
For
like
the linear, it will be same.
Yeah, kx x minus vt whole square,
Right,
the potential, and I'm just moving.
Yes.
And what am I going to get there? Or-
See, the point is, I don't know what you will get there, more or less. If it has a deterministic return, it should have some sort of qualitative same behavior. But I cannot really say more than that. But at least what you see is the distribution for this return time, that remains the same. Because this tau of R, I am not specifying. So, but then it becomes more complicated, right? If you have a potential, a particle return. Right. The first passage part, if you are looking into the first passage as just the first passage aspects, then you can use this renewal framework, which I didn't really have time to go through. And then you also don't need to specify how you are returning. So.
More questions? I had a very quick question. That is,
Please.
in your experiment, so the power of the laser will depend on the trap stiffness, I guess, right? So that,
what I understand that the power is essentially given, it's a given number, but the maximum velocity at which you can keep the particle inside the trap, that depends on the.
No, but that laser is creating a trap of some sort.
Right. That
Like
laser is the
so
only
the power
one.
would determine the stiffness of the.
Yes.
of the trap.
So this is, I think that I did not mention. So this, right, so what you see is here, right? So this power also depends on the stiffness.
It should, yeah.
Yes,
That's right.
that is actually proportional to this conversion factor or something.
Yeah.
There's a relation.
Yes.
Yes.
But then how? So you shine the laser on that particle.
And you keep the laser
and
on.
then you keep it on for some time till you are sure that the particle has equilibrated in the trap.
No. That is not something what we did. We
Then,
just
how do
project
you
the
know
trap.
And then you immediately drag it.
And then no, not immediately. You bring the particle back, keeping the trap on.
Sure, but you give the particle some time in the trap, or you don't give it time, or you just You switch the trap on, the
You
particles
switch the
there,
trap
and then
on,
you just drag it.
then get it back to the origin, and
Okay.
then at the origin you let the particle equilibrate for
Okay,
a while.
okay.
So that is something which you can see it from those trajectories. I see. There were these experimental trajectories which I had. Yeah, I think. Just before that. Yeah, you see this
Yeah,
weight
yeah.
thing?
Yeah.
This weight is essentially the
And that little
equilibration.
green,
Yeah,
that-
yeah.
that-
This,
that's
yeah,
where
that
you
is the
let
one.
it. Yeah.
Yeah, yeah, that is the one.
Okay.
So this return is something finite, but then the weight is. That
Okay.
is what in Chiliberto's experiments.
Any other questions? If not, let's thank Arnav again.
Thank you.